Okay, welcome. Today we're going to be talking about conservation, first of mass and then also of energy. So if you are conserving something, you're saving. So the law of conservation of mass, and hopefully you've heard this before, says that mass cannot be created or destroyed in a chemical reaction. This might be new. You might have heard mass cannot be created or destroyed, period. But we're actually going to learn this year that you can in a different kind of reaction, but not a chemical reaction, which is what we've been talking about. So the mass before and the mass after the chemical reaction should be the same. You're not going to gain any, you're not going to lose any. The same with the elements you start with, should be the elements you end with, the same. So you can't start with cheap elements and do something and all of a sudden get gold or another precious metal. It's just not possible. What you start with is what you're going to be ending with, piece-wise, like element-wise, and we can mix them up and we can make different compounds, but the building blocks have to be the same. So this is what I was kind of getting at. The atoms are rearranged during the chemical reaction by breaking original bonds and forming new bonds. So it's like you've got one box of Legos and that's it. You can only build with what you have. You can't all of a sudden find an extra box or go to the store and buy another box and just add that in. You have one box and that's it. So here's a chemical reaction. Notice we have hydrogen. And for practice, we should put in G for gas. And this is oxygen. And this is G for gas. And this is water, which would be a liquid. Now, don't worry if you don't know how I determined the phases of matter yet. We'll figure that out later. The first thing we need to do is count the number of atoms. So I have two H2s. So if I were to draw them, hydrogen bonded to itself, and here's another one. So that's 1, 2, 3, 4 red dots. So 4 atoms. If you didn't want to draw it, you could just say we've got 2 times 2. Oxygen is a much larger atom, and there's only 2 of them right there. And water, maybe you know what water looks like, maybe you don't. That's okay at this point. Water looks like that. So notice we have, oh look, we have 2 H's. Sorry, we have 4 H's. And we have 2 oxygens in both cases. Notice, even though the original bond here and here, between those, and there's a bond here, those bonds were broken. We made new ones here, 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 here. But we still have the same pieces. Okay, this is where we're going to need to go to the periodic table to find the atomic mass. So you're going to go to the periodic table. You're going to find hydrogen. You're going to look in the upper left corner, and you're going to see a number for atomic mass. Now, the number on the periodic table has a whole bunch of decimal places, and we'll talk about why that occurs later. But if we round that to a whole number, you get, whoops, goodness gracious. I had all that, of course. You'll get 1. So this is the mass. There are 4 atoms, though. So the total mass is 4. And, of course, every mass needs units. So this would be what we call AMU, or atomic mass units. So go ahead and look on the periodic table, find the mass of oxygen, which is 15.9 something, rounded to 16, but there are 2 of them. So we'd have to multiply to get 32 AMU. So the total mass would be 32 plus 4, so 36 AMU, which I'm sure I have on here, but I couldn't help myself. I had to write it. Look over here on the right. So on the right side, you notice we have, again, 4 hydrogens. So each times the mass of 1 is 4. And then we have 2 oxygens, 32. So our total mass would be 36 on both sides. This isn't an ideal world. This is a theoretical world. If you were actually taking hydrogen gas and oxygen gas and putting them together, you might lose some because they're gases, but that would not be because of the chemical reaction. That would be because Humans make mistakes. Lab equipment fails us a little bit. Okay, to switch gears, what is energy? We've already talked about it. Energy is the ability to do work, the ability to supply heat, and it does not have mass or volume. So here's our mass. Remember, this is a quad beam balance. And this we have a grad cylinder. And that looks like a flask of some kind. But wait a second, we don't have volume and we don't have mass. Energy doesn't have that. Remember, everything in the universe is either matter or energy. So this is the energy piece. Excuse me. Hey, this should look familiar. We've already gone through all of these. So you can either look back at the earlier notes, or you can just say, see earlier notes. So we've already talked about these. Just a reminder, here they are. This is not probably all of them in the universe, but this is pretty good for us. Okay, so if you're going to measure energy, you might want to look on table D. Sorry, that's messy. In the metric system, it's joules. Yeah, you should know how to say it. It's metric, named after James Prescott Joule. In America, we use calories to measure energy. This is the conversion factor. So you can see that a joule is smaller than a calorie because it would take 4 and a little bit joules to equal 1 calorie. So that's our conversion factor. This is not on the reference table, but it'd either be provided to you or you could look it up. So what are some characteristics of energy? Now, technically, we've already talked about that. What did I even do? We talked about the characteristics. Remember when we went through and we labeled some of them? One letter, P for potential, and E, it's not E, K for kinetic. So that's what we're talking about here. So you can either have kinetic characteristics, energy that is in use from motion, or you can have potential, which is stored. So we talked about how kinetic would be things like electrical, mechanical. There's a bunch more, so I'm just going to say ... We only talked about 2 being potential, which would be the chemical energy stored within bonds and nuclear energy stored within the nucleus of atoms. There could be others, but for right now, that's all we need to know. And to kind of wrap up, since we started with the law of conservation of mass, we also have the law of conservation of energy. So what does that mean? Well, if the law of conservation of mass said that mass cannot be created or destroyed, then this must say energy cannot be created or destroyed, but it can change forms. So, for example, we have a flashlight. So how does a traditional flashlight work? You would start with chemical energy, which is stored in the battery, because most flashlights require a battery. So once the battery's in there and it's attached, it's placed against those metal leads, you have a flow of electrons, electrical energy, which is when it touches the metal contacts. We have the flow of electrons. And then once it's flowing electricity, what's the whole point? The whole point of a flashlight is there's light from the bulb. Could there be any other forms of energy given off? Why, yes. How about heat energy as a byproduct? So the amount of energy stored here in this battery should be the same amount of energy given off here. We haven't gained any. Maybe we lose some, so maybe we'd lose some energy in the form of heat as opposed to light. But you can only have as much energy as what you start with, which just comes from the battery. Okay, I think that's where we're going to stop for today. Thanks.